Okay, so today we're going to start our series of lectures on transient analysis of second order circuits, where a second order circuit is a circuit that contains two energy storage elements. So today we are going to look at a specialized case, the parallel RLC circuit. So what we're going to be doing today builds off of the transient analysis of RL and RC circuits that we dealt with in circuits 1. So if some of this isn't making sense, you might want to go back and review that. Okay. So let's consider the following circuit. We're going to have a current source, which is providing some amount of current IS, and it's going to be connected to a switch. On this left-hand path, we're just going to have a short circuit. On this right-hand path, we are going to have some resistor R in parallel with some inductance L in parallel with some capacitance C, like so. And the case that we are going to consider, I'm going to call this terminal A and this terminal B. Our switch is closed at position A until T is equal to 0, at which point our switch changes to being closed at position B, effectively disconnecting our current source IS from that parallel RLC network. I am going to define a couple of important quantities here as well that are going to be part of our analysis. So I'm going to call this voltage V of T. And this is the potential difference between the top terminal of our parallel RLC network and the bottom terminal of our parallel RLC network, which means this is also the capacitor voltage. And as we learned in circuits 1, the capacitor voltage cannot change abruptly, meaning that it needs to be a continuous function in time. Let's call this current right here IR. This current right here IL. And this current right here, IC. Okay. So before we get into the nitty-gritty of this, I want to talk our way through things really quickly so that we can have a kind of qualitative understanding of what's going on in this circuit. Okay. So before T is equal to 0, before our switch changes state, our circuit is at DC steady state, right? So we're making an assumption here that our switch has been closed at position A for a very, very long time so that there are no transient signals that we have to deal with. And so our inductor is going to look like its DC steady state equivalent, which is a short circuit, and its capacitor is going to look like its DC steady state equivalent, which is an open circuit. So under those constraints, our current IL of T for all T less than 0 will be IS. Well, since our inductor current has some finite value, that means that our inductor has some amount of energy stored in it. When our switch changes states at t is equal to 0, disconnecting this current source from the RLC network, our inductor is going to serve as the energy source for the RLC network. And so over time, it is going to transfer its energy to the capacitor and the resistor. And this transfer between the inductor and the capacitor and the resistor is the transient response of the network. A very long time after our switch has changed states, the inductor will have fully discharged, meaning that the resistor has converted all of the stored energy into heat, and we should see that all of our currents and voltages are 0, reaching a second DC steady state condition at what I'm going to call t is equal to infinity. Okay, so graphically, our inductor current is going to look something like this. And actually, let me move this axis more to the middle. So here's IL of t. Here's t. So our inductor current is some constant value during this DC steady state condition. Steady doesn't look good. A long point in time after t is equal to 0. The dashed line here. Our inductor current has decayed down to 0. So we're once again at DC steady state. And then we have this region of time here where our transient condition is occurring. So for a simple RL circuit, we know that this response is going to be purely exponential. Since we're dealing with an RLC circuit, that might not be the case. So I'm not going to draw a curve here representing how the inductor current is going to behave from t is equal to 0 out to t is equal to infinity, because that's what we're going to be figuring out next. All right, so during the transient condition, meaning 0 plus is less than or equal to t is less than infinity. We can write a Kirchhoff's current law equation. Actually, let me say this really quickly. So during the transient condition, our current source, IS, is connected to that short circuit over there on the left. And then here we have our resistor, our inductor, and our capacitor like so. Here's our voltage, V of t. Here's our current, IC, our current, IL, and our current, IR. And we can write a Kirchhoff's current law equation at that top right node, which simply states that IR plus IL plus IC will be equal to 0. Since my resistor, my inductor, and my capacitor are all in parallel, they all share the same voltage drop across them, and I can express all three of those currents in terms of that common voltage, right? So using Ohm's law, IR is going to look like, stylus will write, V of t divided by R. My inductor current is going to look like 1 over L times the integral from some point in time where our inductor current is known, which would generally be at 0 naught. I'm just going to write generally T naught here. The T of V of T prime dt prime, where this T prime is a dummy variable representing time because I have T without the prime notation and the limits of my integration. So this is just for mathematical correctness, not anything fancy. Plus IL at T naught plus C dV by dt, and all of this is equal to 0. So what we have here is an integro differential equation. It's a differential equation that contains both a derivative function and an integral function. And generally speaking, these are a little annoying to solve. So what we are going to do is we are going to take the derivative of both sides of this expression. So when I take the derivative of C dV by dt with respect to time, I wind up with a term that is the second derivative of the voltage with respect to time. Rearranging here a little bit. When I take the derivative of the resistor current term, I'm going to get 1 over R times the first derivative of the voltage with respect to time. When I take the derivative of the integral bit, I'm going to have 1 over L times the 0th derivative, or just the voltage. And then when I take the derivative of that IL at T naught, that is a constant, so the derivative of a constant is 0. And now I'm left with a second order differential equation. I could stop here, but I'm going to take this one step further for something that we're going to do at the beginning of next week. And so all I'm going to do is I'm going to divide through by C so that the coefficient of my second derivative term is 1. So that's going to leave me with d squared v by dt plus 1 over RC dV by dt plus 1 over LC V is equal to 0. And this is the homogeneous second order differential equation that describes our circuit. So our goal now is to figure out what form our voltage must have in order for this differential equation to be true. In circuits 1, we made an educated guess that our signal of interest, in this case our voltage, would be an exponential. And because that worked for us in circuits 1, that's what we are going to work with here and see what shakes out. So I'm going to assume that my capacitor voltage will generally be of the form AE to the ST. Okay. So the second derivative of AE to the ST is S squared AE to the ST. Then I'm going to have S divided by RC times AE to the ST plus 1 over LC times AE to the ST is equal to 0. I've substituted in my guess value. And now I'm going to do a little bit of algebra here. There's a common factor of A. Then I'm going to have this term, so S squared plus S divided by RC plus 1 over LC times E to the ST will be equal to 0. So I've done nothing more than just remove the common terms here, and I've split them up in this way so that we can look at this thing piece by piece, right? So our ultimate goal is that this expression is equal to 0. That will be true if A is equal to 0. But if A is equal to 0, effectively everything is equal to 0. So that would imply that we didn't have any energy stored in our system to begin with. The A is equal to 0 solution is effectively what happens to our system if we don't put any energy into it. Everything is 0. So while it is a solution, it is a trivial solution that does not accurately reflect the conditions on our specific system. So that's not going to work for us. The quantity E to the ST will approach 0 if S is negative and we wait for a long time. So that's not really doing what we're looking for either. So instead, we're going to need to look at this bit right here, which is called the characteristic equation for our system. So looking at this characteristic equation, we can see pretty easily that it is a second order polynomial in S, or another way to put it would be it's a quadratic function. And luckily for us, we know how to solve quadratic functions, right? So since this is a second order polynomial, we are going to expect two solutions. So we're going to have one solution, just as a quick aside here. I'm going to refresh you guys' memory on the quadratic equation. So we are going to have S1 and 2 will be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a, where a is the coefficient of the s squared term, b is the coefficient of the s term, and c is the coefficient or the constant term. Okay. So let's look here and say that S1, so this is going to be when we use the positive sign. B in this case is going to be 1 over RC, so we're going to have negative 1 divided by RC plus the square root of B squared, so that's going to look like 1 over RC quantity squared minus 4 times A, where A is 1, times C, where C is 1 over LC. and all of this will be divided by 2. And so what I'm going to do now is I'm just going to make it a little prettier by moving that 2 in the denominator up into the numerator, right? So this is going to become -1 over twice RC plus the square root of 1 over twice RC squared minus, and I'm going to do something a little bit fancy here, the square root of 1 over LC quantity squared. So that's what things are going to look like when I move that 2 from my denominator into the numerator. And now I'm going to define 2 quantities here. So the first will be alpha. Alpha for a parallel RLC circuit is simply 1 over twice RC. This is what's called the Neper frequency. Measured in Nepers, a dimensionless quantity per second. And what the Neper frequency is it represents the rate of decay of our signal. So it is similar to the role a time constant played in our first order transient analysis problems. Okay. Our second quantity that we're going to have, omega naught, is the square root of 1 over LC. And this is what's called the resonant frequency of our circuit or system, measured in radians per second. And this resonant frequency really has a lot of different roles depending on what kind of system that we're looking at. Okay. So in most electrical systems, the resonant frequency means 2 things, and it means both of these things effectively at the same time. The first of which is this is the frequency at which the system will resonate with the largest amplitude for the smallest amount of input energy. And it also happens to be the frequency at which the impedance of the system will be purely real. Okay. We're not really going to use either of those things in this particular context because we are not exciting the system right now. We're seeing how it responds when we take a source away, but we'll deal with both of those other representations later on in this class. Okay. So I can express S1 in terms of alpha and omega naught. Right? So S1 would be negative alpha plus the square root of alpha squared minus omega naught squared. And S2 would be negative alpha minus alpha squared minus omega naught squared. So since we have 2 different values of S, okay, our true solution for VC of t will actually be of the form A1 e to the S1t plus A2 e to the S2t, right? So instead of it being a single exponential function, it's now going to be a combination of exponential functions. Effectively, all this means is that if we have two different natural frequencies, this S1 and S2, we are going to need two different initial conditions, A1 and A2, to figure out how this thing behaves. Okay. So before we move along here, I want to talk about some special cases, right? Because if we look at this expression for S1 and S2, there are really three different situations that we are going to face. All right. So let's talk about our first condition. And this is what we're going to call overdamped circuits. So in an overdamped circuit, S1, actually, let me write this differently. Alpha will be greater than omega naught, which in turn means that S1 and S2 will be real and negative. And so our general response, y of t, will be of the form A1 e to the S1t plus A2 e to the S2t. Our second case is going to be for critically damped circuits. And for our circuit to be critically damped, alpha will be equal to omega naught. Now, this is something that isn't going to show up a lot practically, because we need alpha and omega naught to literally be identical. And because of tolerances and things like that, it's very hard for us to make a true critically damped circuit. But from a design criterion, this is usually what we are trying to aim for. And I'll talk about why that is in a moment when I plot what these three responses are going to look like. Okay? So in a practical sense, it's very hard for us to actually achieve a critically damped circuit, but generally speaking, this is actually what we try to design to. Okay. So if alpha is equal to omega naught, S1 will be equal to S2 will be equal to simply alpha. So effectively, our characteristic equation has a repeated root, okay? So this is going to force us to modify our response equation in order to take into account the fact that we have two initial conditions, which are going to help us solve for the behavior. So for a critically damped circuit, our general response, y of t, will now be of the form A1 t e to the negative alpha t plus A2 e to the negative alpha t. Our third possibility is what we call an underdamped circuit. And in an underdamped circuit, alpha is less than omega naught. So when alpha is less than omega naught, let's scroll up here and look at this expression really quickly. If alpha is less than omega naught, then we're going to have S1 is negative alpha plus the square root of some negative number, and S2 is going to be negative alpha minus the square root of some negative number. And that some negative number is going to be equal in both cases, which means S1 and S2 are complex conjugates of each other. So using Euler's identity, where we have complex conjugate response or an imaginary response, we can use Euler's identity and express our response equation as follows. We're going to have B1 cosine omega dt, and I'll define omega d here in a moment, plus B2 sine omega dt e to the negative alpha t, where omega d is equal to the square root of omega naught squared minus alpha squared. So these are the three different cases that we might see. And so I'm going to plot them against each other generically here, so that we can kind of get an expectation for what these curves are going to look like. So let's start with a critically damped circuit, which I'm going to do that in purple. Okay. So I'm just going to put a purple dot here to let us know that's what this curve is. For a critically damped circuit, we are going to decay relatively quickly. We are not going to experience any overshoot. So in a critically damped circuit, our system hits its final value in the shortest amount of time possible without any overshoot or ringing. Now let's talk about an overdamped circuit, which I'm going to do in blue. It's going to look effectively the same, but it's going to take significantly more time to hit its final value, or in the case of our system, to lose all of its energy, right? So it gets there, but it gets there much more slowly. Lastly, we are going to have a simple example of an underdamped response. And so for an underdamped response, we are actually going to hit our final value very quickly, but we are going to have overshoot or ringing like so, or we finally settle to our final value over an increased period of time. Okay. So these are the three different responses that we might see. Okay. So the next thing that I want us to do is to work a problem here. We're going to work the problem. I'm going to give you the process by which we're going to do this. And then we are going to simulate the problem in LT Spice. So the circuit that I would like us to look at is a fairly simple one. Let's say that I have a 2-amp source Here is a 10 millifarad capacitor. Here's a 10 ohm resistor. Here is a 4 Henry inductor. And let me define some things here. So this is going to be V of t, which once again will be the voltage drop across my capacitor. This is my capacitor current, IC of t, and this is my inductor current, IL of t. When I give you guys a homework, something like this will generally be your starting point, and these are the quantities that I'm going to ask you to solve for at all points in time, and then I might ask you to solve for something else at the end. So that's something else at the end. In this case, let's make it our resistor current, IR of t, and let's also solve for IC of t so that we can see how this is done. And I'm going to throw you guys a smidge of a curveball here. We're going to assume that our switch is going in the opposite direction, meaning that it was closed at A at t is equal to 0, and then switches over to closed at B at t is equal to 0 plus, so that instead of taking our current source out of the circuit, we're adding a current source in. So whenever we faced problems like this back in circuits 1, all that really changed for our analysis was that we now had to analyze the circuit at t is equal to 0, and that's, or excuse me, t is equal to infinity. And that's literally the only thing that's going to change here as well, okay? So our first step will be to analyze the circuit at t is equal to 0 minus. So this is the instant in time before our switch changed states. So at t is equal to 0 minus, we are at DC steady state. Here is our 2 amp source connected to terminal A. Our capacitor is going to look like an open circuit. So here is V of 0 minus. Our resistor is always going to look like a resistor. So here is our 10 ohm resistor. Sorry, I put 4 Henry capacitor here. This should be an inductor, my apologies. And then my inductor is going to look like a short circuit. Here is IC of 0 minus, and here is IL 0 minus. We should pretty easily be able to see by inspection that V of 0 minus will be 0 volts. IL of 0 minus will be 0 amps. And IC of 0 minus will be 0 amps. All of those quantities should be 0 because our current source isn't connected to anything, the resistor, the capacitor, or the inductor. So there's our analysis for step number 1. For step number 2, we're going to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our current source is no longer connected to the short over here. Since the voltage drop across our capacitor was 0 volts at t is equal to 0 minus, it needs to continue being 0 volts at t is equal to 0 plus. So my capacitor at this specific instant in time is going to look like a short circuit. Here is my 10 ohm resistor. Since the current flowing through my inductor at t is equal to 0 minus was 0 amps, my inductor is actually going to look like an open circuit. So here is V at 0 plus. Here's IL at 0 plus. Here is IC at 0 plus. And I'm actually going to move this plus sign down here so it's not overriding each other. V at 0 plus must be 0 volts. IL at 0 plus must be 0 amps. Will always be true. Whatever we have at 0 minus for the capacitor voltage and the inductor current, we must have at 0 plus. So if you ever get a different answer, you've done something very wrong, just to be clear here. And now we can figure out what IC at 0 plus is. And to me, that looks like it's going to be 2 amps, right? All of the current from our current source will flow through the short circuit that's representing our capacitor at t is equal to 0 plus. So we should have 2 amps of current there. For step number 3, we are going to analyze the circuit. At t is equal to infinity. So at t is equal to infinity, we are once again at DC steady state, but our switch is in the same position as it was at t is equal to 0 plus. So our short circuit to the left is going to be disconnected from our current source. Here's our 2 amp source. Our current source is connected to our RLC network. Because we're at DC steady state, our capacitor is going to look like an open circuit. Our resistor, as always, looks like a resistor. Our inductor is going to look like a short circuit. This is 10 ohms. This is V of infinity, IC of infinity, and IL of infinity. And we can solve this one just by inspection as well. So V at infinity here is going to be 0 volts, because since my resistor, capacitor, and inductor are in series and my inductor looks like a short circuit, the voltage drop across that inductor must be 0. So V is equal to 0. The current IL at infinity is going to be 2 amps, because all of the current from the current source will flow through the short circuit representing the inductor. And IC at infinity is going to be 0 amps, because no current is able to flow through the open circuit representing our capacitance. So these are our circuit analysis steps. I understand that this particular example is rather trivial. That is on purpose. I want us to be able to get to what's going to be different for this new style of circuit. So our next step that we're going to do is we are going to calculate alpha and omega naught and determine what type of response we have. So for a parallel RLC circuit, alpha is equal to 1 over twice RC. So that's going to be 1 over 2 times 10 ohms times 10 millifarads. So when I put 1 over 2 times 10 times 0.01 in my calculator, I get 5 neppers per second. Omega naught is the square root of 1 over LC. That's going to be the square root of 1 over 4 henries times 10 millifarads. So on the calculator, I have the square root of 1 over 4 times 0.01. And I also get 5. This thing will write. Since alpha is equal to omega naught, that means this circuit is critically damped. Okay. So for the most part, everything here that we have done is going to be the same for every single circuit that I throw at you. But this last bit, step 5, is going to depend on what we are trying to solve for. Okay. So let me scroll back up so we can look at things here. So I am trying to solve for my capacitor current and my resistor current. Now my capacitor current is fairly straightforward. There's really only one way that I could go about doing that, but my resistor current I could solve for in a couple of different ways, right? So what I mean specifically, I'm just going to do this as a quick aside here. I know that IC plus IR plus IL is equal to 0, which means IR would be negative IC, something I'm already solving for, plus IL, something that I can solve for. So that would be one way for us to do it. Another way would be for us to say that IR of t is just going to be V of t divided by R. This is a little bit easier because we only need to solve for V of t in order to solve for IR of t. We don't need IC and IL. And as we'll see here in a moment, I'm going to wind up solving for V of t in order to solve for IC of t anyway. So I would argue that this is the route that we should use to solve for IR. So, which means we're going to need to know V of t, and we're also going to need to know IC of t. Okay. So these are our two quantities of interest that we're going to use to get everything else we want. And this will make a little bit more sense here in a moment. Okay. So I have made a table for you all. I put it up on Moodle, so I'm going to bring it up for you right now so we can see it. If you go to class meeting number 9, there we go. I've uploaded this table entitled it Table of Parallel Series RLC Responses. This is going to be what we are going to use a whole heck of a lot in this class, particularly for this section of the course. So I've brought up the table here, and I have effectively summarized today's background lecture and actually the background of what we're doing on Friday into a single table. Okay, so if we have an overdamped circuit and its parallel, alpha is given by 1 over 2 RC, omega naught is given by 1 over root LC. I gave us the expression for y of t. I also included the y at infinity term, so I'm making the assumption here that we have a total response problem. If we don't, the y at infinity term goes to 0. I also went ahead and determined what the derivative is of that expression. You'll see why here in a moment. And then I defined what S1 and S2 are for this particular system. For our critically damped circuits, which is what we're going to be dealing with here in a moment, I have my expression for y of t. I also have my derivative expression. For my underdamped circuits, I have my y of t. I have my derivative expression. And then I also remind you of what omega d is. Okay. So we're going to build our first equation using this y of t expression. So step number 5 will be to determine our quantities of interest. And we are always going to want to do this in a specific order. Okay. So we want I'm trying to think of how to put this succinctly. Our first step is always going to be either a capacitor voltage or an inductor current. So since we're trying to find our capacitor voltage, that's what we're going to have here. So we can say that V of t, because we have a critically damped circuit, will be of the form A1t e to the negative alpha t plus A2 e to the negative alpha t plus b at infinity. This is literally exactly what I have in the table, and I'm just replacing y with the quantity that we're solving for, which is our voltage here in this case. So at t is equal to 0, and I'm going to put 0 plus here, but it doesn't, well, it will matter for certain other things, so we'll get in the habit of putting 0 plus. My first expression here is going to go away, right? Because if I'm multiplying by t and t is equal to 0, a1 times 0 times e to the negative alpha t goes to 0. A2 times e to the negative alpha t is just going to go to a2, right? Because e to the 0 is 1. So plus v at infinity. So going back to our analysis at 0 plus, we saw that V was 0, V at infinity was 0. So we have 0 is equal to A2 plus 0, which means our A2 term is 0 volts. So we have one of our two coefficients figured out. Now, for our second step, we're always going to want to do the derivative-based relationship for whatever quantity we did in our first step. So that means in this case, I'm going to be looking at capacitor current. Okay. So capacitor current is C times the derivative of our voltage. So I'm going to have C times negative alpha A1 T e to the minus alpha t plus A1 minus alpha A2 e to the negative alpha t. Just to make sure we understand where this is coming from, I'm literally just looking at my derivative-based relationship. Hopefully you guys can see my cursor moving over it here from my table. I'm not ever going to make you guys do these derivatives by hand. I've done them for you to save you time and energy. Okay. So our first equation is going to come from this guy. Our second equation is the derivative-based relationship. All right. So we're going to look at what happens to this guy at t is equal to 0 plus as well. So IC at 0 plus, C is going to stay. So this term is going to go to 0 because we're multiplying by t again. So anything times 0 is equal to 0. And so all we're going to be left with is C times A1 minus alpha A2, because e to the negative alpha t goes to 1. So that means, let's see, so IC at 0 plus was 2 amps. So we're going to have 2 amps is equal to 10 millifarads times A1, which we don't yet know, minus alpha, which was 5 nepers per second, times A2, which was 0 volts. So it looks to me like A1 is going to be 2 amps divided by 10 millifarads. So 2 divided by 0.01 is 200 volts per second. Just to be super clear here on these units, the first thing is that we know that A1 needs to be in volts per second because A1 is multiplied by time and we're trying to get a voltage. So that's one way to look at it. But a millifarad, just to remind you guys, is a amp second per volt. So we're going to have amps over amp second per volt. So the amps cancel each other and the volts can move from here up to here, leaving us with volts per second. So dimensionally, it's going to work out for us, right? From this, right, we know what A2 is. Let me put a box around it. And we know what A1 is. So we can now start reconstructing our signals. Right? So V of t is going to be A1 200t e to the minus alpha, which was 5t, plus A2, which was 0. So this means this whole next term is going to be 0, plus V at infinity, where V at infinity was 0, which means that's going to be 0. So this is our voltage, 200t e to the minus 5t. From this, IR of t, something that we were trying to find, is just V of t over 10 ohms, the value of our resistor. So that's going to look like t e to the minus 5t amps. So that's one of the things that we were trying to solve for. For our capacitor current, IC of t, effectively, we're going to use this expression right here to get our coefficients, right? So for my first coefficient is going to be C. Actually, let me write this out. Times negative alpha A1 T. I'm going to rearrange this slightly. Negative alpha C A1 T e to the minus alpha T plus C A1 minus alpha A2 e to the negative alpha T, where we know what alpha, C, and A1 are, right? So alpha was 5, so negative 5 times C, which was 0.01, times A1, which was 200. It's going to look like negative 10t e to the minus alpha t. And then I'm going to have C, which was 0.01, times A1, which was 200, minus 5 times 0. It's going to look like 2, so that'll be plus 2 e to the negative. Since I know alpha, I'm going to put 5 there. Let me fix that really quickly. Amps. There's my second equation. Okay. So give me just a moment here to plug in my keyboard, and we're going to simulate this circuit. All right, so I'm going to build this circuit in LT Spice really quickly. So I need a current source. It's going to be a 2 amp source, direction up. Then I need my capacitor. That's 10 millifarads. My resistor, 10 ohms. My inductor, 4 henries. Let me just wire up the bottom here. Generally speaking, I put my ground node at the negative polarity terminal of my capacitor. So that's going to be down here at this bottommost node. And let's see, we're solving for IR and IC, so I can leave everything alone from here. So one thing that I am going to need to do is I'm going to have to put in a SPICE command to tell the circuit how to behave. So effectively, I'm telling the circuit what was going on at t is equal to 0 minus instead of simulating it. And then I'm simulating the circuit for t is equal to 0 plus and beyond. So I'm going to put in my initial conditions by doing dot IC, and the voltage at, actually, let me fix this. So this is how I usually do it. I label the positive polarity terminal of my capacitor as VC, and then I put in that SPICE command. So dot IC, the voltage at node VC should be equal to 0 volts at t is equal to 0 minus. Control M to give me a new line. Dot IC, the current of the inductor, so that's L1, was 0 amps at t is equal to 0 minus. Let's put this over here. And then I'm going to do a transient analysis. So let me edit my simulation command. Let's see, alpha was 5 per second. So let's run this for 2 seconds, which might be a little long. And run my simulation. We want our, what do? I'm going to add a second plot plane here. See this in a moment, why I'm doing this in a moment. In the topmost plot plane, I'm going to put my capacitor current. And in the second plot plane, I'm going to put my resistor current. Okay. And so now I'm just going to maximize this thing so we can see these two plots. With the top plot plane selected, I'm going to type, or I'm going to go to add trace, and I'm going to put in a mathematical expression. I'm literally going to put what we solved for our capacitor current to be. If I'm remembering correctly, this was -10 times time times the exponential of -5 times time plus 2 times the exponential of -5 times time. And so what just happened is that my red curve here, which is our analytical solution, completely overlaps the green curve from our simulation, which means we analyze the circuit correctly. A couple of key points here to mention. You need to look at the scale on the left-hand side, right? So it runs from +2 amps to -4 amps. Over here on the right-hand side, it runs from +2, to the same thing, -4. These scales need to be the same thing. If the scales are different, it can artificially look like you have the wrong answer, right? So if I change this scale on the left-hand side from going from 2 to -0.4 to 2 to, let's call it -1, now they don't look like they match up, even though we did it correctly. And it's because the scales are different. So you really, really need to pay attention to that. I get a whole heck of a lot of questions about, oh, I swear I'm doing this correctly. You are, you just didn't check the scales. Okay. So let's look at our results for our resistor current, right? So if I'm not mistaken, this was going to be, I think it was 20, but let me double check here really quickly. Yeah, 20 times time times EXP of -5 times time. And this blue-green curve completely overlapped our blue curve. Our scales are the same on both the left-hand side and the right-hand side. So both of our analytical solutions were correct. Okay. So this is how you can use LT Spice in order to make sure that you've done your analysis correctly. And I'm going to ask you to do this for effectively every one of these circuits in the homework problems that I will be uploading today. Speaking of things that I'm going to upload today, because we were only able to work a single example problem, I am also going to upload 3 more example problems, just handwritten solutions or whatever, to give you an example of how you would do that last step effectively for an overdamped circuit, another critically damped circuit, and an underdamped circuit, so that you will have examples of all of those available to you to help you while you're doing your homeworks and stuff like that. All right, I talked for almost the full hour and 15 minutes today, so unless anybody has any questions, I'm going to let you all go. All right, I'm not hearing anything, so I will see you all for series RLC circuits on Friday morning. Have a great rest of your day.